this video, we're going to talk about conditional probability. We're going to look a little bit closer at the probability of two intersecting events, and then we're also going to introduce the concept of independence. So sometimes the likelihood of an event taking place can change based on the occurrence of another event. For example, the probability of a person having lung cancer changes if that person also smokes. If a person is a smoker, they may be more likely. If they're not, then they may be less likely. So whether or not the event is achieved that a person smokes will impact the probability that that person has lung cancer. So this concept is called conditional probability. So conditional probability is the probability of the occurrence of an event A, given that another event that we'll call B has occurred. So our notation for conditional probability of specifically an event that we'll call A, given B, is written as A vertical line B. So we read this as A given B. So probability that event A occurs, given that B has already occurred. So it's going to be defined as the probability that both events occur. So in other words, the probability of the intersection of these two events. The thing that mainly changes here is the denominator. So normally the denominator for a probability is just the sample space. It's the size of the sample space for our particular experiment. What's changing here is now we're defining the denominator as the probability of B. In other words, it's the probability of the event that's already occurred. So essentially what's happening is we're taking what we used to think of as the entire sample space and we're restricting it to just the outcomes representative of the event that has already occurred. So think of like a two-step process. So step one is event B has already occurred. What that means is we've now taken the whole sample space and we've only restricted that to some portion of the sample space, just those outcomes representative of event B. And then we're taking the probability of A, given that B has already occurred. In other words, just looking at the outcomes associated with A that are in that fraction of the sample space associated with the event that already occurred. So we're restricting the sample space to a smaller size, and we're just looking at outcomes within that smaller section of the sample space. So let's look at a couple examples. We're going to look at normal probability, and then we'll talk about how this looks in terms of a conditional probability. So a pointer is spun once on a circular spinner where each wedge is labeled 1 to 6. The probability assigned to the pointer landing on a given number is listed in the table below. So in other words, we're not assuming that it's equally likely to land on any one versus the other. It's based on the actual probabilities we have here. So the probability that we land on 1, so E is our event, and then the probability of E. The probability that we land on 1 is 0.1. The probability that we land on 2 is 0.2, and so on and so forth all the way up to 6. So our first question is, what is the probability of the pointer landing on a prime number? In other words, 2, 3, or 5. Okay, well, the probability that we land on 2 is 0.2. The probability that we land on 3 is 0.1. And the probability that we land on 5 is 0.3. We could think of applying the principle for a union in this case. Think of this as 3 events. These 3 events are all mutually exclusive. So if we spin one time, we could land on a 2 or a 3 or a 5, but not all 3 at the same time. So these 3 events would be mutually exclusive. That means if we want the probability of these 3 as a union, then we can just sum up their individual probabilities. So that would be 0.2 plus 0.1 plus 0.3, which is 0.6. Okay. Another question, what is the probability of the pointer landing on an odd number? Well, what would that look like? That could be a 1, a 3, or a 5. Again, those are all going to be mutually exclusive. So if it lands on a 1, it can't land on a 3 or a 5, and same thing for 3 or 5. Any individual outcome in here is mutually exclusive of the others. So the probability of each of those outcomes can just be summed, and that comes out to 0.5. That's the probability of that event. Now, here is a conditional probability. We're taking similar probabilities but we're rewording them. So our first question is, what is the probability of the pointer landing on a prime number given that it landed on an odd number? Okay, so what we're assuming is that we've already landed on an odd number. What we're essentially doing is we're taking the whole sample space and we're just breaking it down and restricting it to the outcomes associated with that event that has already happened, and landing on an odd number. So if we think of the whole sample space as being all the different outcomes we could get, all the different spins from 1 to 6, the event that has already occurred is that we've landed on an odd number, which means we now eliminate the possibility of landing on 2, landing on 4, or landing on 6. We're just looking at the outcomes associated with the event that has already happened where we land on an odd number. So our conditional probability is defined as the probability that both events occur. Well, event A, the one we're really interested in, is landing on a prime number, but the event that has already occurred, that's restricted our sample space, is landing on an odd number. So the numerator for our probability is the probability that both events have occurred, that we landed on both a prime number and an odd number. Well, which numbers are both prime and odd? Well, 3 is prime and 5 is prime, and they're also both odd. So those are going to be both odd and prime. So the probability that we land on something that's both prime and odd is going to be 0.1 plus 0.3. Those are the probabilities for the outcomes representative of this intersection. Now the denominator is where we apply the restriction. So the restriction is that we're not looking at the whole sample space, not everything from 1 to 6. We're only looking at the outcomes representative with that event that's already happened, the event where we landed on the odd number. So rather than dividing by the whole sample space's size, we're dividing by the probability associated with the event that's already occurred, landing on an odd number. Well, we determined that that probability is going to be 0.5. So our denominator is going to be 0.5. So the whole probability comes out to 0.4 divided by 0.5. And if you do that division, that's going to be 0.8. Now let's look at another one. What happens if we have the same events, but we change the order in which the events occur? So what's the probability that the pointer lands on an odd number, given that it landed on a prime number? In other words, imagine it landed on a prime number first. That's restricting our sample space. So rather than looking at the whole sample space, all the possible spins from 1 to 6, we're putting a condition on this probability, and we're saying that the condition is that we specifically landed on a prime number already. So we're restricting the whole sample space to just the outcomes associated with landing on a prime number. Well, remember, our prime numbers are 2, 3, and 5. So we're just looking at that portion of the sample space, which would then exclude 1, 4, and 6. So just 2, 3, and 5. Okay. So that's going to be our denominator. It's the probability associated with that particular event that's already occurred, and we determined that that was 0.6. Now the numerator is going to be the overlap of the two events, and you'll notice the two numerators are actually going to be the same. Something that's both prime and odd is also something that's both odd and prime. So rearranging the order of the two overlapping events is not going to change the probability that they occur. The only thing that changes from one conditional probability to the other is going to be that denominator. Which event occurred previously is going to restrict the sample space in different ways. So if we restrict it to what was odd to begin with versus what was prime to begin with, then we're restricting it based on a different denominator. And notice our final probability comes out to something different. So our numerator is 0.4, our denominator is 0.6, since that was the probability of landing on something that was prime, that was the event that had already occurred, and 0.4 divided by 0.6 is approximately 0.667. So those two values are conditional probabilities. They're probabilities of a particular event, the event that we get a prime number and the event that we get an odd number, but it's probabilities conditional on, or conditional dependent upon the condition of the fact that we already landed on a particular event, that we already achieved a particular event, and that we're no longer looking at the entire sample space, just the segment of the sample space associated with the event that's already occurred. Okay, let's look at another example. So city records produce the following probability data on the likelihood of a driver being in an accident on the last day of a Memorial Day weekend based on whether or not there was rain. So in other words, was there an accident? Was there not an accident? Was there rain? Was there not rain? All the data for all the different combinations. Okay, so these are all considered to be probabilities. So how do we interpret a table like this? Well, our two events are going to be the event that there was an accident, which we'll call A, and the event that there was rain, which we'll call R. So rain is R, no rain is R prime. Remember, that's the complement. And then accident is A, no accident is A prime. In other words, the complement of that event. And then based on the intersections in this table, it tells us the different probabilities based on different combinations of events, based on intersections of the event of rain, the event of an accident, or their complements, or any combination in between. So the first probability we want is the probability of an accident, rain or no rain. In other words, what's the probability that we have an accident regardless of rain? Well, if you look at the probability for an accident, that's going to be in that first column. The total probability for having an accident was determined to be 0.040. So that's going to be the probability that we have an accident. Notice you could also determine that by summing up the probability of an accident in case there was rain and the probability of there was an accident in case there was no rain. The sum of those two possibilities gives us the total probability of it having an accident, rain or no rain. Okay? Find the probability of rain, accident or no accident. In other words, what's the probability that we have rain regardless of whether or not there was an accident? Well, here's the rain category. The total probability that there was rain is going to be 0.360. So again, we could decompose this into two values. Here's the probability that we had rain and an accident. Here's the probability that we had rain and no accident. If we sum those two probabilities, that sums up to 0.360. Okay, find the probability of an accident and rain. In other words, the probability that we have both an accident and rain. Well, this is an intersection. This is the intersection of the event accident and the event rain. So here's rain and here's accident. The intersection gives us a value of 0.025. So the intersection of these two events has a probability of 0.025. Okay, now here's our conditional question. Find the probability of an accident given rain. In other words, what is the probability that we ended up having an accident given that there was already a rainy day? So the rain had already started. What's the probability that we end up having an accident given that we know it was going to rain? Well, remember, go back to the definition. So both events are occurring. Rain has already occurred and the accident is going to occur as well. So our numerator for our probability is going to be the intersecting probability. The rain occurred and the accident occurred. And we know that probability is 0.025, so that's going to be our numerator. Now the fact that this is a conditional probability, again, just means that we're restricting the sample space. So we're only looking at all the possible outcomes associated with rain having already occurred. Well, what's the probability that rain has occurred, that conditional event has already occurred? Well, we determined that that's 0.360. So that's going to be the denominator for our probability. So rather than looking at all the possible outcomes, we're just looking at the outcomes associated with rain having occurred. So given that rain occurred, the probability that there's an accident is going to be the probability that both occurred divided by the probability that that conditional event occurred. And that's going to come out to 0.069. Okay. So that's a little taste of conditional probability. We're going to look at it a little bit more, but again, the general idea is think of taking the sample space And instead of looking at the whole thing, we're just looking at the subset of the sample space associated with something that's already happened. We're breaking it down and restricting it to a specific set of outcomes associated with something that's already occurred. And then we're essentially applying another event based on the event that's already occurred. So the conditional probability formula can be rearranged to handle situations where we want to know the probability of an intersection. So kind of like there's a little bit more to the probability of a union. We have to worry about mutual exclusivity. There's a little bit more in terms of the probability of an intersection, particularly when we talk about a sequence of events when multiple outcomes could occur and there's multiple ways for a particular event to be achieved, multiple outcomes associated with our event. So if you were to imagine taking our conditional probability formula, suppose we knew the conditional probability, but we wanted to know the probability of the intersection. Suppose this was our unknown. Well, we could solve for this unknown. We could develop a formula for that just by rearranging this formula. If we were to multiply both sides of the equation by that denominator, by the probability of B, which would move it over to the other side, we now have isolated the probability of the intersection, which again we're thinking of as the unknown. So we have a formula for the probability of the intersection based on what we know about conditional probability. It's going to be defined as the probability of B times the probability of A given B. Now keep in mind, intersection A intersect B, B intersect A doesn't change anything. So there's two different versions of conditional probability that could allow us to solve for this particular intersection. If we were restricted to the outcomes associated with B and we were conditional on B, then this would be the formula we used. Now, if instead we were restricted to the outcomes associated with A and we were looking at conditional probability upon A, then this would be the version of the formula we would use. Keep in mind, A and B are really just arbitrary labels, so we're just thinking of which event has already occurred versus which event is then dependent upon that as a condition for occurrence. So we can use this concept, this idea of multiplying two probabilities together to find the intersection of an event. So what I want you to think about when we talk about an intersection is think about it as a sequence of events. It's one event and then another, but I want you to think of it literally as one event as a first step and then the next event is a second step. When we talk about the conditional probability, we're thinking about what's happened based on that event occurring. So how has the situation changed? How has the next probability changed based on the fact that the first event has already occurred? That's what we're going to think of when we talk about conditional probability and we talk about the intersection. Multiplying together our two probabilities is going to give us the probability of the intersection, but as we follow a sequence of events, and we want the intersection of those events in that particular sequence, we have to monitor the situation from one event to another. How has one event changed the situation, and what's then the impact on the next probability? We'll put this in the context of an example, and that'll make more sense, hopefully. So in order to deal with these issues where one event affects another and there's sort of a trickle-down effect, it's helpful to have a visual. So we're going to use what we call a probability tree. This is also something we used when we talked about the multiplication principle for counting. This allowed us to organize all the different combinations if we want a visual for how different combinations are connected to one another. If we have multiple choices in a multi-step process, each choice can then be associated with the others in a particular way, and we drew a tree diagram to represent that. We can also do that with probability. So we're going to draw the diagram associated with the outcomes. Think about all the different outcomes following our sequence of events. So one particular event occurs and then another event occurs. And then based on what happens at any step, we're going to assign our probabilities to each branch. In other words, starting with one particular outcome, what's the probability as we branch off to another outcome that follows in the sequence? So all of this is really, really vague sounding. Let's put it in context. So for example, 2 balls are drawn in succession without replacement from a box containing 3 blue balls and 2 white balls. We want to represent this situation, and then we're going to answer some questions about it. So first, let's look at the questions, and then we'll go back and we'll talk about the diagram. So our first question is, what is the probability of drawing a white ball on the second draw? Okay, so we have to think about all the different ways that could look. How could it look when we draw a white ball on the second draw? And then our next question is going to be, what is the probability that at least one of the balls drawn will be blue? Okay, so let's talk about the tree diagram. How do we form a tree diagram for this? Well, here's the box. Okay, so we have a box that has 3 blue balls and then 2 white balls in it. Okay, so what is our experiment? What are we actually doing? Well, we're drawing 2 balls. So it's a 2-step process. We draw 1 ball, we take it out of the box, it doesn't go into the box. That's what without replacement means. And then we draw a second ball. So what we need to do is we need to analyze what's going to happen from our first draw and then as we go towards our second draw. But one thing I want you to keep in mind is because there's a finite number of balls in this box and because we're not putting the balls back in, once we make one draw, it then affects what's going to happen the next time. It affects how likely any particular outcome is based on what happened before. So every time we draw a ball out of this box, essentially the situation changes. The box's contents change. So the probabilities are very closely impacted by what happens from draw to draw. So we need to go through and we need to analyze what's going to happen in each situation just based on the prior outcome. Now we're only drawing 2, so we don't have to go super far, but I want you to think of this as a model that you could then apply in other situations if you were to keep going. This kind of tree can branch out further and you keep going in the same way. Okay, so we start and then we're drawing 1. So what are the possibilities in terms of drawing our first draw? Well, either we're going to draw blue or we're going to draw white. So blue 1, B1 is going to be draw a blue the first time, and then W1 is going to be draw white the first time. Well, what's the probability that we draw blue versus the probability that we draw white? We're going to label those 2 branches with the probabilities. So the box is as is, nothing's changed from the very beginning. What's the probability that we draw blue? Well, there's 3 ways to draw blue out of the total of 5 draws, 5 different balls to choose from. So the probability that we draw blue is going to be 3 out of 5. Now, what's the probability that we draw white? Well, there's 2 ways to draw white out of the 5 balls to choose from. So the probability that we draw white is going to be 2 out of 5. Now notice if you added those 2 probabilities together, 3/5 and 2/5, you would get 5/5, which sums up to 1. Not a coincidence. Every time you write the probabilities for one particular set of branches, they should always add up to exactly 1. Think of it as an event and then the complementary event. The branches should exactly add up to be 1. In this case, they do. Okay, so those are the probabilities for our first draw. Now, as we look at the second draw, because we're drawing 2 balls in succession, as we look at the second draw, we have to analyze the impact of what happened on the first draw based on which path we're going on. We have to figure out what are all the different paths we could take and what happens along that particular path based on what happened before. In other words, based on us being conditional on the previous event occurring or not occurring. Well, let's start with the first path. So we drew a blue. Let's say we drew a blue. What could then happen? Well, we could draw another blue or we could draw a white. So either we draw a blue for the second or we draw a white for the second. But we have to analyze these 2 probabilities. What's the probability of drawing another blue? What's the probability of drawing a white? Based on the fact that we drew a blue the first time. In other words, think about how the box has changed based on the fact that we're following that path where we started by drawing blue. Well, the easiest way to think about how it's changed is just cover up the one that's drawn. Imagine removing it from the box. So we drew a blue, okay? This is now the box once we get to the second draw. So we drew a blue, that blue is now gone. Once we look at the next set of probabilities, we're looking at those probabilities based on what's still in the box. Most notably, there's no longer 5 balls in the box, there's only 4. So whereas our first probabilities had a denominator of 5 because we had 5 to draw from, our next probabilities are going to have denominators of 4 because we now only have 4 to draw from. But specifically, we drew blue. So not only does the total change, but also the number of blue balls available changes. So suppose we draw blue for the second draw. Well, how many ways are there to do that based on the fact that the first one drawn was blue and we've already taken that one out of the picture? Well, there's 2 ways remaining to draw blue out of the 4 remaining possibilities. So that probability is going to be 2 out of 4. Well, now suppose we drew blue the first time, but we draw white the second time. That's the other possibility. Well, how many ways are there to do that? Well, there's 2 ways to draw white. The number of white balls didn't change, so there's 2 ways to draw white, but now we only have 4 to draw from. So the probability of drawing white is also going to be 2 out of 4. Now again, notice, sum those up. 2 over 4 plus 2 over 4 adds up to 4 over 4, which is equal to 1. So those 2 probabilities for those branches adds up to 1. Okay, so if we were to draw one blue and then another blue, this would be the path we follow. If we were to draw one blue and then a white, this would be the path we would follow. Okay, so those are all the possibilities starting with a blue draw based on drawing 2 balls. Now, what if we drew white first? So we know white will occur 2/5 of the time based on there being 5 balls, 2 white balls in the box. Okay, so we drew white the first time. Now we want to analyze the second draw. So if we drew white the first time, that means 1 white ball is no longer in the box. So this is now the box, 1 white ball absent. Well, from that first draw, what could happen? Well, we could either draw a blue next, or we could draw another white. What's the probability of each of those outcomes based on the fact that now we assume we drew white the first time? Well, again, notice most notably that we now no longer have 5 balls in the box. We only have 4 in the box. So our denominator for our probability is going to change to 4 in both cases. The numerator is also dependent, though, on the fact that now it wasn't a blue that we drew, but it was a white that we drew. So the situation has changed in a different way based on what we're assuming was the first event that occurred. So if we drew white the first time, what's the probability that we then draw a blue? Well, there's 3 ways to draw blue out of the 4 total possible draws. So the probability that we draw blue for the second ball is going to be 3 out of 4, given that we drew white first. Now, what's the probability that we then draw a second white? Well, there's only 1 left to draw from out of the 4 in total. So our probability is going to be 1 out of 4. Again, 3 out of 4 plus 1 out of 4 sums up to 4 out of 4, which sums to 1, it reduces to 1. So each of these probabilities explains what happens at each step in this 2-step process. But the second set of probabilities, notice they differ. So second blue versus second blue, the probability is different based on what previously occurred. These 4 probabilities associated with the second set of branches, these are conditional probabilities. These are the probabilities based on what happened the first time around. So if we drew a blue the first time, these are the associated probabilities conditional upon that blue. If we drew a white the first time, these are the probabilities conditional on the white that was drawn the first time. As we follow any given sequence, though, we're following the probabilities associated with that particular sequence. So I recommend going through and trying the probability tree again on your own. Make sure you understand how this is created. Think about physically what's happening to the box each time, to the contents of the box, how much is in there, what's actually in there, and make sure you can label this probability tree on your own and you understand where these probabilities are coming from. Now we can use this tree to answer questions about different probabilities. So our first question is, based on this scenario, what's the probability of drawing a white ball on the second draw? Well, what could that look like? White ball on the second draw. Well, here's the two white balls on the second draw. We have to think about the entire path though. So it's possible that we could get a blue the first time and then a white the second time. It's also possible that we could get a white the first time and then a white the second time. So there's two different sequences represented by this particular event. So the event in question could be blue 1 intersected with white 2. That's a possible way that we could draw a white ball on the second draw. Or it could be white 1 intersected with white 2. That's another way to draw a white on the second ball. So when we look at the probability of this whole event, we have to consider the probability of both of those possible outcomes. Now what we want to know is, what's the probability of each of the outcomes in this event? These are mutually exclusive. There's no way we follow path 1 and follow path 2 at the same time. So if we know the probability that path 1 occurs and we know the probability that path 2 occurs, we can just add those together, and that's going to give us the total probability, essentially using that idea we used when we found the probability of a union. But how do we determine the probability of each individual path? Well, that's where this formula for the intersection is going to come into play. So the probability that we drew blue the first time and then white the second time is going to be the product of the probabilities along that path. So it's the probability that we got the first draw that we wanted, and then it's the probability that we got that second draw based on following the path that started with that first draw. So it's just the product of the probabilities associated with the two branches along that path. So the probability of blue 1 intersected with white 2 is going to be the probability of blue 1, which is 3/5, times the probability that our second draw was white, given that we first got a blue draw. I'm not super worried about can you do that part. I'm worried about can you do this part. Do you know what the probabilities are going to look like? So think about it as just multiplying the probabilities for each step in the process. This is the probability for step 1, and then from step 1, this would be the probability for step 2, based on the fact that step 1 has already occurred. So 3/5 probability of getting a blue, and then from that blue, 2/4 probability that we get a white. Of course, you could have reduced that to 1/2 already if you want, or you can just wait till the end. So we multiply our two fractions together. Remember, if we're going to multiply fractions, you just go straight across numerator and denominator. So 3 times 2 is going to give you 6, and then 5 times 4 is going to give you 20, which reduces to 3 out of 10. Now we're not quite done, because remember, there's two different ways that we could draw a white ball on the second draw. It's possible that we draw blue first and then white, or we could draw white first and then white. So we have to consider the possibility that we went along the other path. Well, what would be the probability in that situation? Well, again, we're going to multiply together the probabilities for each step in that process. So the probability that we drew white the first time was 2/5, and then if we followed the path to that second white, which is associated with this event, then the next probability would be 1/4. So based on drawing white the first time, the probability that we then draw a second white is 1/4. So 2/5 for the first step multiplied by 1/4 for the second step is going to give us the probability for that particular outcome for white 1 and then white 2. So that comes out to 2 out of 20 or 1 out of 10. We're going to sum the probabilities for the two specific simple events, for those individual events representative of those individual intersections, which is going to come out to 4 out of 10. So 3 out of 10 to get a blue and then a white, 1 out of 10 to get a white and then another white. We sum those, and that comes to 4 out of 10, which reduces to 2 out of 5. Okay, so there's one example where we would follow the path based on this probability tree. Now let's use it in another situation. So what's the probability that at least one of the balls drawn will be blue? Keywords here, at least. Well, what could that look like? At least one is blue means exactly one could be blue, or also both could be blue. We could have the possibility where both are blue. So let's go back and look at our tree. Okay, so we want to analyze all the different ways that this event could occur. How many different outcomes are associated with this event? Well, we could have blue 1 and blue 2. That's at least one ball being blue. In this case, 2 of them are, but 2 is at least 1. We could have blue the first time and white the second. That's at least one being blue. Or we could have white the first time and then blue the second. That's at least one ball being blue. The only path not associated with this event would be drawing 2 white balls. In that case, neither of them is blue, so it does not fall under this event. So we have 3 different ways, 3 different outcomes associated with this event, and we want to determine the probability for each. Each of these paths is mutually exclusive, so then we just add up each individual probability for each individual outcome. So let's assume we had blue first and then blue again. Well, the probability that we get blue the first time is 3/5, and then based on that blue, the probability that we get another blue then is 2 out of 4. So we multiply those probabilities together, and that's the probability that we have that intersection, that we followed that sequence. So 3 out of 5 times 2 out of 4. Now what about blue first and then white second? So we have blue, that's a 3/5 probability, and then white second is based on that a 2/4 probability. So also 3/5 times 2/4. And then the only other possibility that fits this event is going to be white first and then blue second. So white first has a 2/5 probability, and then blue second, based on drawing white first, then has a 3/4 probability. So 2/5 times 3/4 is going to be our probability. Now what you'll notice is that actually all of these products are the same. So numerators are both 3 and 2, denominators are both 5 and 4. So we end up with 6 out of 20 3 times. So we're adding it up to itself 3 times, which is the same thing as multiplying by 3. So that ends up coming out to 9 out of 10, or 0.9. So that's the probability that we end up with one being blue. Now, how do you know you have to go through and analyze something like this? You have to think about whether or not going from one step in a process to another results in probabilities that are going to change. The reason the probabilities changed from one step to another in this problem is because of that without replacement component. The fact that we started with this box, and then as we draw, we're not putting balls back into the box, is the reason that this was kind of a special situation. Once we draw one from the box, we change the situation, we change the contents of the box. We essentially change the sample space for the next step in the process. So we have to indicate that as we consider how the probabilities change from one step in the process to the other. What if it didn't say without replacement? What if it just said you're going to draw them and then you put them back in the box? What if you did replace them? Well, you wouldn't have to worry so much about the probability, you wouldn't have to worry so much about the tree. Why is that? Well, say you drew a blue the first time, okay? We know there's a 3/5 probability that we draw a blue the first time. But if you're going to put it right back into the box after you do that, then the probability of your next draw has no dependence on what you did the first time. If you put the ball you just drew back into the box, then you're just as likely to draw anything as you were before, because the box looks the same as how it started. It's this without replacement component that changes the situation from step to step. When you don't replace what you drew, the box changes from step to step. And so you have to analyze what is the effect of each draw. What happens if you draw blue the first time? What happens if you draw white the first time? What's the then trickle down impact to the rest of the problem? So look for this kind of issue when one particular step in a process, if you're talking about a sequence of events, one particular event is then going to somehow impact the next event. We have a term for that phenomenon where one event impacts the other. We call that independence versus dependence. So when the probability of one event occurring does not depend on the probability of another event occurring, then the two events are said to be independent of one another. One occurring doesn't make the other event either more likely or less likely. It doesn't change anything, so they're independent. Now, when the probability of one event occurring does depend on the probability of another occurring, then they are dependent. In other words, if one event occurring can either be more likely or less likely, depending on what happened beforehand, then the two events are dependent on one another. So if we were to think about this example where we were drawing the balls, in which situation are two draws independent, in which situation are two draws dependent? Well, suppose the balls are drawn without replacement. In other words, based on the situation we've described. Okay. When you draw the first ball, say you drew blue the first time, notice that changes the likelihood of drawing blue or drawing white the second time. How do we know this? Well, if we were to draw white first and then draw again, the probabilities are different for our second draw. The reason we know there's some dependence here is based on the fact that the probabilities change for the second draw. If we draw blue the first time, then the next two draws are equally likely, or the next two options for drawing are equally likely. Whereas if we draw white the first time, the next draw from the two options, they're not equally likely. So following one path for the first draw versus the other then takes us to a situation where the probabilities change. So this second draw, this second event, is dependent on what happened to the first time. It's dependent on which of the first two options for events we followed. So if we're drawing balls and not replacing them, then the two events are going to be dependent on one another. The probability of the second draw, whether you get blue or white the second time, changes based on whether or not you got blue or white the first time. Now, what if we drew balls but then we replaced them? In that case, the two events are independent. Why is that? Well, again, we talked about it just a moment ago, but think about it this way. Say you drew blue the first time, okay? So now you have two balls that are blue, two balls that are white. But then you're going to put the blue back in there, which means the second time you draw, you're now drawing from the box as if nothing happened previously. There's no way to determine what happened before, and whatever happened before has no impact on your next draw because the box is right back to where it started. Same thing if you drew white. If you drew white the first time, okay, now you have four balls, three are blue, one's white, but now you're going to put that white ball back into the box. Now the box is right back to where it started. So the next draw you make doesn't depend on what you drew before because the box looks exactly the same as how it started. So if we're replacing things, if we're then resetting the situation so that it looks exactly the same as how it started, and one particular event occurring doesn't affect the next event that occurs, then we would say that the events are independent. Now, in a situation like this, we can just analyze it logically. It's easy to see overall whether or not one event affects the other based on the situation we're in. But sometimes it's not as obvious. Sometimes it's not always going to be obvious whether or not one event affects another or if they're independent of one another. So there's actually a way to determine algebraically whether events are going to be dependent or independent just based on their probabilities. So say we're comparing A and B in our sample space. A and B are independent. In other words, one occurring does not affect the other if the following statements are true. So number one, the intersection, if the probability of the intersection is just the probability of our product, or the product of our probabilities, then we know that the events are not dependent. They are independent of one another. In other words, if you can determine the probability of the intersection of both events occurring, and if you can determine the probability of the individual events occurring, then if the probability of the intersection happens to be the same as the product of the individual probabilities, if those two expressions are the same, then you know that the events are going to be independent of one another. By definition, if you just think about independence versus dependence, we can also say that the probability of A given B is the probability of A, and the probability of B given A is the probability of B. What does that mean? Well, the first one, if you just want to think of it this way, this is the probability that A happens given that B happened. In other words, given that somehow B happened and now we're restricting the sample space in a particular way. If this probability based on a restriction is the same as the probability of the event with no restrictions, if having this event occur ahead of time doesn't actually change anything, if this probability comes out to the same as the probability with no restrictions at all, then we know that B occurring didn't have any impact on whether or not A occurred, which by definition means that the events are independent. Same thing if we flip A and B. If A occurring, then B occurring, doesn't change anything. If the likelihood that B occurs, given that A already occurred, is the same as just the likelihood of B occurring with no particular conditions on it, then we can also say that the events are independent. It just means that the other event occurring ahead of time didn't actually change how likely the current event is or is not to occur. So let's look at a couple examples. Now, in most cases, we're going to use this first definition for independence. We calculate the probability of both events occurring, and if we can calculate the individual probabilities of the individual events and take their product, as long as those two values are the same, then that means our two events are going to be independent, if we can't just look at them logically and determine independence. Okay, so in two tosses of a single fair coin, show that the events heads on the first toss and heads on the second toss are independent. What does this really mean? Well, this is essentially saying show that one toss's outcome is independent from the other toss's outcome. Logically, this should be true. Logically speaking, whether or not you get heads or tails the first time should have no impact on whether or not you get heads or tails the second time. But we want to prove this algebraically. So we're going to verify it using this first relationship. We want to show that the probability of both events occurring is the same as the product of the two individual probabilities of the two individual events. So event A is heads on the first toss, and event B is heads on the second toss. Well, let's of course start with our sample space. So we're tossing two coins. So our sample space is all the different combinations of heads and tails. So we could have heads, 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 tails, tails, heads, and then tails, tails. So event A is heads on the first toss. What does that actually look like? Well, that could be heads and then heads, or it could be heads and then tails. Those are the two outcomes described by heads on the first toss. Now, what about heads on the second toss? Well, that could be heads and then heads, or it could be tails and then heads. So those would be the two events or two outcomes associated with heads on the second toss. So what do we want to do now? Well, we want the probability of the intersection. We want the probability of the individual events. We want to compare. So what's the probability of the intersection? Well, what is the intersection of these two events? What outcomes represent both A and B occurring? In other words, heads on the first toss and heads on the second toss. Well, the only way that occurs is if we get heads, heads. So there's only one way for these two outcomes to overlap out of the four total possibilities represented in our sample space. So the probability that both A and B occur is going to be 1 out of 4. Now, what about the probability of A and the probability of B individually? And then we take their product. Well, the probability of A has two outcomes representative of that event. So two outcomes out of the four possible in the sample space. So the probability of A is going to be 2 out of 4. The probability of B, well, B has two associated outcomes out of the four possible in the sample space. So the probability of B is also 2 out of 4. Those two fractions are both going to reduce to 1/2. And of course, when we multiply fractions, multiply straight across. So 1 times 1 is 1, 2 times 2 is 4. Notice that the probability of the intersection and the probability of the product, or the product of the probabilities, I said it again, the product of the probabilities of the individual events, both of those expressions come out to the same value. So as long as they come out to the same value, that proves algebraically that A and B are independent. Logically, they should be, because again, logically speaking, whatever you get the first time shouldn't have any impact on what you get the second time, and vice versa. So they should be independent, but this just proves it algebraically. Okay, let's look at another couple of examples. So a single card is drawn from a standard 52 card deck. Test the following events for independence. In other words, are they independent or are they not independent, aka dependent? So event E is that the drawn card is a spade, and event F is the drawn card is a face card. So what we want to know is, does getting a spade make it more likely or less likely to get a face card? Does it have an impact on that, or vice versa? So we're going to use that same definition of independence. We want to check the probability of the intersection. We want to check the two individual probabilities and take their product. If those values are the same, then the two events are said to be independent. So let's think about the intersection first. So event E is we draw a spade. Event F is we draw a face card. The intersection means both events are occurring at the same time. So in other words, we're drawing both a spade and a face card. Well, how many outcomes represent both events occurring at the same time? In other words, both a spade and a face card. Well, in order to fall under both, it would have to be face cards that are spades. Well, how many of those are there? Well, there's the king of spades, the queen of spades, and then the jack of spades. So there are 3 different outcomes associated with the intersection of those two events. So 3 ways to overlap in those two events out of 52. Why is it out of 52? Well, remember, the experiment is drawing a single card. So the sample space is all the different outcomes we could get out of that 52 card deck, which is going to be 52. So the probability of our intersection is going to be 3 out of 52. Okay, now to that we want to compare the individual probabilities, then multiplied together. So what's the probability that we get a spade? Well, how many ways are there to get a spade? There's 13 spades in the deck out of 52, so the probability is 13 out of 52. And what about getting a face card? Face cards, again, are jacks, queens, and kings. There's 3 per suit, and there's 4 suits. So there's 12 of those in the deck out of 52. So the probability of getting a face card is 12 out of 52. That's going to reduce to 1/4, and then 3 out of 13. And so if we take that product with the reduced fractions, we get a numerator of 3, we get a denominator of 52. So we're comparing those two values, the probability of the intersection and the product of those individual events' probabilities. Because those two values are the same, we can determine that E and F are independent. In other words, if we draw a spade, it makes us no more or no less likely to get a face card. If we draw a face card, it makes us no more or no less likely to get a spade. The probabilities are the same regardless of whether or not one event occurs before the other. Now, what if the first event is we draw a club, and the second event is that we draw a heart? Does one impact the other? Does drawing a club the first time then impact how likely we are to draw a heart? Does drawing a heart the first time impact how likely we are to draw a club? That's the question we want to answer. So let's analyze our intersection. In other words, both E and F at the same time. So what outcomes are represented with drawing both a club and a heart at the same time? Well, let's think about it. We're only drawing a single card. We're drawing one card, so we have one chance to meet both of these outcomes. So we want a card that's both a club and a heart at the same time. Well, by definition, a card can't be a club and a heart. Clubs are one suit in the deck, hearts are another suit in the deck. So you can't have a card that's both at the same time. Club cards are black, heart cards are red. There's nothing that's going to be both at the same time. So the probability of both events happening at the same time, the probability of the intersection, is going to be 0, because it's impossible for both of these events to happen at the same time. If E happens, then F can't happen. If F happens, then E can't happen. So the probability of the intersection is 0. Now, what about the individual probabilities? We want to compare that product to this probability that we just found for the intersection. Well, what's the probability of E? In other words, the probability that we get a club. Well, there's 13 ways to get a club out of 52 cards to draw from. And then the probability of F, same kind of thing. There's 13 hearts to choose from out of 52. So both of those probabilities reduce to 1/4. We take their product and we get 1/16. So the probability of the intersection is 0. And then the probability of, or the product of the probabilities, I did it again. The product of the probabilities is going to be 1 out of 16. So because these two values are different, because they are not equal, that tells us that our two events are dependent. Why are these two events dependent from a logical standpoint? Well, think about the events occurring in sequence. So say we did E first. We draw a card and it's a club. So imagine taking that one card and pulling it out of the deck, okay? The fact that you drew a club the first time now means that the ratio of cards in the deck changes. So if you draw a club the first time, there are 13 hearts still, but now it's out of 51. Because you drew a club and you now reduced the number of clubs available, but the number of hearts didn't change, there's now a different ratio of cards in the deck. So it'll be 13 out of 51 for a heart rather than 13 out of 52 for a heart. So the probability of getting a heart at that point has changed. Same thing vice versa. If you draw a heart the first time, now there's one fewer heart in the deck. So the ratio of clubs to the total changes because the total number of cards in the deck has changed. It doesn't actually work that way with the spades and the face cards. And if you think about it the same way in terms of what happens if you draw one versus the other, you can think about it the same way and you can analyze the probabilities in the same way. So these last two events would be dependent. One happening or not happening will determine how likely the other is to happen. So they have dependence upon one another. So we talked about independence, we've talked about intersection, and most importantly, we've talked about conditional probability. Again, think of conditional probability as being probability dependent on something having already happened. So rather than looking at a whole sample space of outcomes, now we're just looking at outcomes associated with an event that has already occurred, and then analyzing another event in that context.